Okay, so the discussion in the previous section about standard delta G and standard voltage, of course, takes us to the next topic, which is the non-standard voltage, right? Because most of the time when we do this reaction, we're not using standard conditions, which is pressure of 1 atmosphere and molarity of 1 molar for the aqueous solution. A lot of times we might be using some other molarity or some other pressure of gas. So we can relate the non-standard voltage with non-standard delta G as follows. So keeping in mind that delta G is itself is equal to delta G standard plus RT ln Q. So if delta G is negative NFE, then delta G standard is going to be equal to NFE naught, right? And that's what this equation is showing. It's basically a rewriting of the delta G equation in terms of voltage. And if I divide both sides by negative NF, then I should get this equation right here. This is actually a really important equation. This is called the Nernst equation, and it allows you to calculate non-standard voltage, assuming you know the standard cell potential, which of course you can calculate from your standard reduction potential values, and you know the ratio of products to reactant that you have for that non-standard condition. Okay, the RT over NF ln again could be converted to a log base 10 as opposed to a log base E, and the Nernst equation could be rewritten to look like this. So E is equal to E naught minus 0.0592 volts over N being the number of moles of electron, log of Q. Okay, so you can either use the top equation or the bottom equation, either way, whichever one you find a little easier to apply. All right, so let's take a look at how to apply the Nernst equation to do some calculation. Here it says, in a test of new reference electrode, a chemist constructs a voltaic cell that has a zinc half cell and a hydrogen half cell under following condition where the zinc concentration is 0.01 molar, the proton concentration is 2.5 molar, and the pressure of the hydrogen gas that's generated is 0.3 atm. They're asking us to calculate the E cell. Now this problem, you're going to have to think through a little bit what the cell looks like, right? It doesn't give you the value of the E naught, so you're going to have to look that up first. We can see here that we have two things. We have the zinc cell and we have the hydrogen cell. So we're going to have to combine them to see what numbers would make sense, what process would make sense, who's going to be oxidized and who's going to be reduced. Okay. So if you look up the information in your standard reduction potential value, the idea is you have to find something that generates an E that is positive, because that's what's spontaneously going to happen. Once you find that, then you can use that reaction and the Nernst equation to help you calculate the E at non-standard conditions. So when I look up my standard reduction potential, I find that the oxidation of zinc will give me 0.763 volts positive. Again, when you look up the standard reduction potential, you're going to see a reduction reaction, which is negative, but then you have to flip it to make it positive. And then reaction for the acid and the hydrogen is just your standard hydrogen electrode that we discussed previously. And that, of course, has a reduction potential of 0 volts. So if you add these together, you got a positive E cell. Again, that's your requirement. Okay, so I made this positive where I oxidize zinc and reduce my proton. So if I add the entire reactions together, I already have 2 electrons for both, so it's already balanced. I just need to add the overall reaction, so it looks like this. So that's my actual reaction that I'm running, right, that generates this E cell. Now the question then is, if I want to use the Nernst equation, which looks like this, to calculate my voltage under non-standard condition, I'm going to need my E naught, which I have here. That's my 0.763. But I also need this whole thing right here, RT over NF ln Q. So first thing is I need to calculate my Q. Well, what is my Q for a reaction like this? You're going to have to think back to your equilibrium chapter. Q is the ratio of products of a reactant under non-equilibrium condition, right? So it'll be concentration of zinc times concentration of hydrogen divided by concentration of H plus. Remember that this other zinc here is a solid, okay? So that doesn't factor into your Q expression. So I'm going to need those 3 numbers. I was given all 3 numbers. However, the number for the hydrogen gas is given in pressure in atmosphere. So I need to convert that to concentration. To do that, I do it on the side here using the ideal gas equation, PV equals nRT. So N over V, which is concentration, is going to be P over RT. And then putting in the numbers that they gave us, plus some of those constants, I got 0.01226 molar for the concentration of H2. So now I take the concentration of zinc, concentration of H2, divided by the concentration of H plus squared, since the coefficient is 2. Plug in the numbers there, gives me a Q value of 1.96 times 10 to the minus 5. Okay, once I have that, I take that Q and put it in here. I plug in all the numbers that I need here. Remember that that could be written as just 0.0592 divided now by 2. Where's that 2 come from? That's the number of moles of electrons. So remember, in the reaction, we have 2 electrons that's being generated, so that's 2 moles. I changed the base here to base 10 for the log because I'm using that 0.0592 in the top. And putting all those numbers in, I get non-standard cell potential of 0.902. So in fact, when the standard condition gives me only about 0.76 volts, the non-standard condition gives me 0.902 volt. And you can probably see why that is. That's because you have a lot of reactant. Remember that the concentration of the H plus here is 2.5 molar, and then the concentration of the products are pretty small, right, to begin with. So it makes a lot of sense that if you have a lot of reactant and you have very little product, you're probably not that close to equilibrium, right? So you're going to shift to the right, which means making product. So if you're going to make product, that means that you're going to generate a larger volt than you expect at standard condition. Okay, so again, think about how all of those concepts of standard condition, non-standard condition, shifts in reaction compared to equilibrium position. All of those are connected together in this question. All right, I want to get into a discussion a little bit about what the interpretation of the standard versus non-standard cell potential is, okay? You know, when we use a battery, which is, again, the most common application of a voltaic cell, we see that when we use it, eventually the battery dies, right? So what does that mean when we say a battery dies? So we want to look at it with respect to the cell potential and the non-standard cell potential, right? And so let's imagine that we have a battery that's made up of the zinc and copper pairing that we've looked at throughout this chapter. Okay, the standard cell potential for that pairing is 1.1 volts. So that would be how much voltage you will get out of that battery if you were to have every species at 1 molar, the aqueous solution, right? So the concentration of the copper and the concentration of zinc ions are both at 1 molar. But let's say we're starting with a battery where the zinc is at 10 to the minus 4 molar and the copper is at 2 molar. Okay, so remember that standard condition, both of these guys are at 1 mole, right? That's the meaning of standard condition. It's like aqueous solution are at 1 molar concentration. So you can see that if I compare to these numbers, the copper ion is bigger than 1 molar. The zinc ion is much smaller than 1 molar. So that means that they're really not that close to standard condition, right? So in this case, they should be moving more towards the product. Again, compare both these numbers to 1. The copper is bigger than 1. It's on the reactant side. The zinc is less than 1. It's on the product side. So the reaction should be going more towards the product, which means we expect the E at that condition, because this is non-standard, should be greater than E naught, okay? And we can calculate it. So if you can calculate it using the Nernst equation, just as we did in that previous problem. You calculate it, you'll find that your E is 1.23 volts, which makes sense. It's bigger than the standard condition voltage of 1.1 volts, okay? And that makes sense because your Q here is less than 1, okay, when you calculate it. Now, as you run your battery, what do you expect to happen? Well, more of this reaction will occur, so the copper concentration will go down, the zinc concentration will go up, right? As you're running the reaction, as you're using your battery, some of the electron is going to flow, so we expect reactant to come down, product to go up. So at some point, as you're using it, the voltage is going to drop, right? So if you use it so that the two concentrations are both equal to 1 molar, then at that point you are at standard concentration for both species. So your E and E naught are equal when they're both equal to 1 molar, when the concentration of those two ions are equal to 1 molar. Okay, so the voltage is dropping. Initially it's 1.23 volt, now it's 1.1 volt. If you keep using your battery, eventually you'll get to a point where this number, the copper ion, drops some more, the zinc ion is going to go up some more. So the battery voltage is just going to keep dropping. So here I just pick a situation where my zinc concentration now is 1.5 molar. Remember that we started earlier with the zinc being only 10 to the minus 4 molar, very small number. Now it's gone to 1.5 molar. The copper initially was at 2 molar. Now it's gone to 10 to the minus 5 molar. So it's very little copper left, right? So at that point, the voltage is still 0.95 volts. So still reasonable. But as you can see, the battery is no longer provides as much energy as when you started, which is at 1.23 volt. Eventually, if you keep running the battery, what do you expect to happen? Well, the voltage will drop to 0, right? Eventually it will go to 0. So that, in fact, is what happens every time you use a battery. You start at a voltage that's pretty high at the beginning, and as you use the battery, the voltage keeps dropping. So this is a plot of voltage to the value of Q in this case. And the reason it's plotted against Q is because Q measures how much product relative to reactant. So as you're running your reaction, as you're using your battery, more products are being made, more reactants are consumed, your voltage keeps dropping. Eventually, your voltage will drop to zero, which is when your reaction has reached equilibrium and your Q is equal to K.